Don't be an American. An American looks at those numbers and goes, well, 16's less than 23.
I don't think they're significantly different.
Tell me why!
Because they're within, I know we don't, the margin, the only thing I'm thinking of is the margin of error.
Good for you.
Because I'm thinking that if we were to make a long graph, they would be in.
What's a long graph called? More technical.
Sorry.
No, I love that. I love that you're calling it a long graph because you're visualizing it. You're visualizing it. What's that called? 2 words. Starts with C. Ends with confidence interval. That's the one. We got to make a confidence interval, right? If you've drawn a random sample from a population, you don't want to stop at just your sample, right? You want to take the sample and extract it out to your population. The way you do that is with a confidence interval. You're 95% confident, which means you got it, girl. You got it. It's part of the language. It's part of the communication. You want to be 95% confident or something that you've got this range of values that you think the parameters between. Absolutely. Absolutely. So now, here's what I'm going to do this. I don't want you to do it. I'm going to do it up here on the screen, but I don't want you to do it at your desk. I'm going to explain why in about 2 minutes. I will make 2 confidence intervals. One for cantilevers and one for V's. Is that fair? One for cantilevers, one for V's. Okay, here we go. Jen, question? Oh, your discussion. Okay, so I'm going to go to that same sheet we were using earlier. Here's cantilevers. This is going to be feet. Stopping distance. X bar for cantilevers is 23. S is 2. Sample size is 21. Which means, assuming that my data was a randomly drawn sample, I am 95% confident that a cantilever set of brakes is going to stop me between about 22.1 feet and 24, so 22 to 24 feet. I'm 95% confident I'm going to stop in that range. 22 to 24, remember that. 22 to 24, remember that, okay? 22 to 24. Okay, here we go. Here we go, 22 to 24. I'm now going to do the same thing for V brakes. 16.4, 1.1, I guess I shouldn't use all that significant, should I? Just do 16, 1, and 20. For V brakes, I'm 95% confident that I'm going to stop between about 16 feet and 16 and a half feet, maybe call it 17 feet. So I'm 95% confident I'm between 16 and 17 feet. Cantilevers, 22 to 24.
I guess they are.
V 16 to 7. Now, Katie, what you were looking at before, I loved. You were looking at the standard deviation. Bless you. Yes, you were looking at the standard deviation. But the standard deviation only governs what group of numbers? But which particular group of those distances? The sample that you drew. That sample standard deviation is only the sample standard deviation of the sample you drew. As soon as you take that and apply it to the population, assuming you checked off all these boxes happily, that means you get to divide that by the square root of the sample size, which brings the margin of error down. That's the whole beauty of inferential stat, is you get that shrinking of margins of error as you get larger and larger samples. Is that fair? Now, there is one concern I have, because it looks like they're doing great. 16 to 17 feet, 22 to 24 feet. That's like a 7-foot difference or something, or not quite 7-foot difference, 5-foot difference at least. The only problem I have is what's called confidence. I've now lost confidence, haven't I? And I asked you a question like this on your exam. We have now run 2 simultaneous confidence intervals. Both at which confidence? 95%. The problem with running 2 confidence intervals at 95% is we are no longer at 95% confidence, are we? We are now at 95% squared, which is closer to 90% confidence. What I want to start talking about today is how to take these numbers and turn them into one confidence interval. Put them both as the same interval. So what we're going to go from is, let's come over here again. We've talked now about a single proportion and a single mean. A single proportion and a single mean. What happens when you have two is not two. What happens when you have 2 proportions or 2 means? Now before we get into the crunching, I don't want you to worry about the crunching because the crunching will be taken care of. I want you to know what this is going to look like. Because I see this fear. I see fear in faces. I don't want fear in faces. Nothing to be afraid of. This doesn't look any different. This doesn't look any different than the original confidence intervals. Check this out. If you're testing a single proportion, your confidence interval looks like this. P hat minus the margin of error to P hat plus the margin of error. That's all it is. If you're testing a single mean, it looks like X bar minus the margin of error, X bar plus the margin of error. What would it look like if you were simultaneously testing two averages? How many X bars do you now have? How many X bars do you now have? You've got two, don't you? You got two X bars. Let's label them. Let's label them. You're going to have X bar 1 or X bar 2. You can also name them different if you want to. A lot of times, this is where you start hearing about control groups. What's a control group? What's a control group? Good luck, good luck. What's a control group? What would the control group be in my experiment we just did?
The cantilever brake.
Yes, why?
Because you're controlling that brake, you're controlling the other brake, like you're stopping.
Yeah, but why would the cantilever? This is a good question.
Okay.
A good answer too, by the way. Why is the cantilever the control group? Because that's the one that came on the bike
Oh yeah.
originally. That's like a status quo stasis, right? That's the one that was always there in the beginning, and I'm going to see if an experimental interaction will affect anything. Is that believable? See what's good? That's the difference there. It's what came on the bike originally. If V-brakes came on the bike originally, that would be my control group. I changed my cantilevers. If I went from cantilevers to discs, cantilevers would still be my control group.
Okay.
Sometimes you have more than one experimental group. I will never do confidence intervals on more than one. You'll have 1, 2, and 3, and 4, and 5. You can have different groups, one control group and a bunch, but we'll just stick with 2. So what do you think we're going to do to these two averages to see if there's a difference? I think I just gave the answer away, actually. If you're going to see if there's a difference, what are you going to do, Derek? You're going to subtract them. So where X bar itself was in the confidence interval here, it won't just be X bar anymore. The statistic you're going to be interested in is going to be X bar 1 minus X bar 2. You're going to be looking for the difference in the average. The difference in the average of the two groups. Of course, what you're really interested in is the parameter. The parameter is what you really care about. The parameter is mu1 minus mu2, because hopefully you buy the fact that the populations have averages too. There is an average stopping distance of all cantilever brakes, and there's an average stopping distance of all V-brakes. So the idea is we don't know what those are. We're trying to estimate them with these. Okay, so far? So what would the confidence interval look like in symbols? In symbols, if we were to set it up. Use those guys over there as an example. These are kind of the templates, right? These are kind of the templates. That's a single proportion confidence interval. There's the single mean confidence interval. What would the confidence interval look like for two averages? The difference between two averages. Who wants to give it a whirl? What would be on the far left side over here? Go ahead, Shannon.
Parentheses bar x minus bar x1 minus bar x2
Yes.
minus margin of error.
Oh.
And then you do u.
Less than. If I do less than.
No, less than.
Okay, good.
Right, u. And then another less than.
Oh, 2 mu's, right? 2 mu's. Is that okay?
Oh.
Because remember, I'm looking at a difference between two of them. Does that make sense?
Yes.
So you're going to have the difference of the averages, because that's what I'm really interested in, right? Is there a difference between these two brakes? Okay, keep going, keep going.
Less than the x bar 1 minus x bar 2 plus margin of error.
I love the parentheses. I'm going to put those in just for the hell of it, even though mathematically you don't need it.
Right.
It's gorgeous. That's what you're going to be doing right there. It was wonderful. Yes, golf clap. That was wonderful, golf clap. Yes. That was so freaking good. That's, oh, Derek, go ahead. I'm sorry, I'm jumping in the way. That's what you need. Now, just so you know, too, to share this with you, on your flow chart, it's there.